Hello there, everyone, and welcome to another exciting edition of HL Chemistry Flipped Classroom. I'm Mr. Los. Today we're going to introduce you to organic chemistry. Yes, it's a little scary. It can be a little bit difficult, but we're going to start on this journey today, and eventually we're all going to rock this, okay? But it takes some diligence. It takes a fair bit of memorization, but if you keep up with the material and you really try, I think we can get there. So, sometimes you might hear someone asking, is this chemistry organic? If they're a little particular about the type of food they eat or the type of chemistry they perform, yes, this is organic chemistry that we're studying. What is organic chemistry? Well, it's basically the study of carbon-containing compounds. Carbon can form all kinds of bonds. It forms 4 strong, stable bonds, usually with a variety of other elements, which means carbon can put itself together in all kinds of crazy combinations. There's millions of more carbon-containing compounds than all other types of compounds combined. And in fact, it's carbon's ability to form all these fancy things that we have to thank for life even be able to exist. If carbon couldn't form all these fancy bonds, we couldn't get all the fancy things we need to have life, DNA, proteins, everything else. So the fact that carbon exists and can form all these fancy bonds and make all these fancy compounds, if it couldn't, we wouldn't be here talking about it because we wouldn't be alive. So since there are so many millions of compounds, as a chemist, you can't possibly just say, I'm going to learn about all of these compounds and learn how they work and learn their properties. It's just not possible. So instead, and also keep in mind, some of these molecules are very, very large. So instead, we focus on specific areas of the molecule that we call functional groups. And as organic chemists, we learned that molecules with certain functional groups are going to behave in similar ways, relatively predictable ways. So a functional group is a grouping of atoms on an organic molecule, and it's going to give certain characteristics, like I was kind of saying. What we also can observe as chemists is there can be a group of organic molecules called a homologous series. These are a group of molecules that differ by only one CH2 group, and I think you'll see what I mean by CH2 group when you look at some examples. And the properties of a homologous series can change in a particular fashion or a somewhat predictable pattern. So between looking at functional groups and looking at homologous series, and we're going to go back into all this stuff in more detail later, but we can make some guesses about how a molecule is going to behave and what kind of properties that it's going to have. Another thing you'll see in organic molecules is a R. A R stands for some generic carbon chain of any length. It could be 1, 2, 3, 4, 5, 500 carbons long, and we always assume that there's hydrogens in every possible spot, unless we say otherwise. And again, you're going to see some examples, and I think you'll see what I mean. We further group organic molecules into classes that contain a particular functional group. Now, this is something that IB is kind of picky about, the distinction between class and functional group. There's a lot of overlap. They're kind of the same thing. In some cases, the class name differs from the functional group name. In some cases, it doesn't. This is all stuff we'll talk more about, but class versus functional group. The class is the grouping of compounds, and a functional group is something kind of more specific, I guess you could say. But there is overlap between the terms. So here's an example right here. There are a group of compounds called alcohols. That is the class. So there are a variety of compounds that we call alcohols, and they are going to share certain characteristics. All alcohols contain this OH connected to some number of carbons. Now, an OH, anywhere we see it in an organic molecule, is called a hydroxyl. So the functional group is hydroxyl. The class of chemicals is called they're called alcohols. So here we have the first 3 simplest alcohols: methanol with 1 carbon, ethanol with 2 carbons, and what's called propanol with 3 carbons. This is an example of a homologous series. The only thing that is different about these is exactly 1 CH2. This has no CH2s, this has 1 CH2, and this has 2 CH2s here in the middle. So they're basically just a longer and longer alcohol. So kind of more and more carbons with a little OH in the end. So that's what a homologous series is. Now, this particular molecule, that is ethanol. You may know it. It is the active ingredient in beer and wine. It makes people do funny things. Now, we got this gal here. I don't know how much ethanol she's been consuming. She does look like she has at least 1 alcoholic beverage in her hand. You know, I love this gal here. Oh, apologize for the bell. I love this gal here. You know, she's living her best life, is what I would say. Uh-oh. Sorry about this. Let me pause it. Yeah, so this fella here, I'm guessing he has consumed some ethanol. He's a little confused about which stair he should be going up. And this guy here definitely had one too many beverages, probably at this very establishment that he's at right now. So watch out for ethanol. It can cause some bad things to happen. So another thing about functional groups that's going to come up is they can be considered primary, secondary, or tertiary. And how you tell if a functional group is primary, secondary, or tertiary is you look at that functional group and you look at the carbon that that functional group is attached to and how many carbons are attached to that carbon. And I'll show you some examples in a second. But if the carbon is attached to 0 or 1 carbon, it's going to be primary. Basically, these are going to be functional groups that are on the end of a chain. A carbon chain are always going to be primary. 2 other carbons are going to be secondary. These are going to be middle of chain functional groups. And then tertiary carbons are not only going to be in the middle of a chain, but there's going to be another carbon associated with it. So hopefully you'll see what I mean when we look at some examples here. So here are 3 alcohols. This is a primary alcohol. So determine whether a alcohol is primary, secondary, or really any functional group. So here's my functional group right here, and it's attached to this carbon, and I'm asking myself, how many carbons is this carbon attached to? It's attached directly to 1, right? 2 if you count this one, but it's directly attached to 1, so that means it's primary. This one, if we look at this little hydroxyl right here, it's attached to a carbon, and this particular carbon right here is directly attached to 2 carbons. 2 carbons and a hydrogen, that makes it secondary. Here, again, we look at the functional group, we look at the carbon that that functional group is attached to, which is this carbon. This carbon right here is attached to 1, 2, 3 other carbons. That makes it tertiary. So again, primary is always going to be on the end of a chain. Secondary will be in the middle of some kind of carbon chain. And tertiary will also be in the middle, but there has to be another carbon associated with this carbon there. So these ones here, why don't you take a second and you can see what you think and determine whether these are primary, secondary, or tertiary. Okay, so this one, this carbon is attached to 2 other carbons. That's secondary. This carbon is attached to no other carbons. That's primary. This carbon is directly attached to only 1 other carbon. It doesn't matter what this business is going on over here. So this is still a primary. Here's another couple of examples. You can try these. Okay, so this one is tertiary. Here's the hydroxyl. This particular carbon is attached to 3. This one is secondary. This carbon is attached to 2 other carbons, so that one is secondary. So what we're going to move into now is how these molecules are named and a little bit about how you draw their structures. So the first ones we're going to start off with are hydrocarbons, and we've talked about these before, but hydrocarbons are organic molecules that contain carbon and hydrogen only. And so a particular type of hydrocarbon called alkanes are hydrocarbons with no double bonds. And you can predict their molecular formula from Cn equals H2n plus 2. Definitely something we need to know. So if you understand how many carbons that something has, you basically will always know how many hydrogens are going to be associated with it if it's an alkane, if it has no double bonds. So for example, an alkane with 5 carbons, the N there would be 5. 5 times 2 is 10, plus 2 is 12. So an alkane with 5 carbons we know would have the molecular formula C5H12. Something you hear about alkanes is they're said to be saturated because they contain the maximum number of hydrogens given the number of carbons that they have, as opposed to other ones, as we'll see, which will have fewer hydrogens than the maximum. One thing that's true is that carbon will, with a couple of rare exceptions, pretty much always forms 4 bonds. So that's one way we can keep track and kind of know, that's one way you can kind of keep track of how many hydrogens are going to be in a structure and other things like that. So alkenes are carbons that have at least one carbon-carbon double bond. And when there's a double bond between two carbons, since carbon can only form 4 bonds, it's going to have 2 fewer hydrogens. And believe me, we'll see lots of examples of this, and you'll see more what's going on. So the general formula is CnH2n, assuming one double bond. So for example, if an alkene had 5 carbons, it would only have 10 hydrogens, because there's going to be a double bond between 2 of those carbons. And then ALKYNES, which you say alkynes, are going to contain at least one carbon-carbon triple bond. So, for example, if we had 5 carbons, N is 5, so there would be 2 times 5 is 10, minus 2 is 8. So it would be C5H8 if we had a triple bond in there. So alkanes, alkenes, alkynes, all types of hydrocarbons, it's just alkanes, no double bonds, considered saturated. Alkenes and alkynes are considered unsaturated because there potentially could be more hydrogens associated with that. Yes, that's what I said. So if there's no double bonds, there's more hydrogens that you can attach since carbon always forms 4 bonds. So these are both unsaturated. Now, the great thing about kind of learning more chemistry is some of these like really funny chemistry jokes that are flouting around in there. You understand them better. So this chemistry cat here says, "Do you know any organic chemistry jokes?" And he says, "I know all kinds." So actually, I really like that one. Yeah. Knowledge is power, kids. Once we know these things, we can get more jokes. Drawing organic molecules. So the structure of organic molecules is critical. In our chemistry class so far, if we're talking about like calcium chloride, CaCl2, we don't really need to worry so much about what the actual structure of that ionic lattice is. Most of the time, it doesn't really matter. But with organic molecules, it's really important because how things can be put together, basically the same molecular formula in many cases can be put together in a variety of ways. They're going to make completely different substances with different properties. And this is something that we're going to focus on later more. Those are called isomers. So a molecular formula alone, like C5H12, like I was just talking about, that doesn't really cut it. Because there are several, I think there's at least 3 different molecules that have that exact molecular formula, but are different substances. So there are some different ways of representing organic molecules because, again, the structure has to be there. We can have, these like 3-dimensional computer model type thingies or actual 3-dimensional models like our little model kits like we've used before. We can have what we call full structural models, so everything is drawn out so we can see the exact structure. Here's a homologous series, methane, ethane, propane, so a homologous series of alkanes. They're only differing by 1 CH2 group. There's something called condensed notation, which is just a little bit more kind of put together, a little bit easier to draw. What you're going to see is that these molecules can be a little tedious to draw because there's lots of carbons and lots of hydrogens. So organic chemists have tried to find ways to kind of like shortcut all of this drawing. And then the last one here is skeletal structure. So notice we're getting kind of like more and more kind of a shortcut way of drawing it. We go from the 3D models to this, to these condensed notations, and then to the skeletal, which is an even bigger shortcut. So to show you what I mean about those, I don't have my normal setup here. I'm going to have to try to draw on the board behind me. Hope you can see it okay. So here I have 3 different organic molecules. This is kind of a condensed type notation here. Not quite as fully expanded out as that full structural formula. So the way we do the skeletal notation, literally we draw lines. And because of the fact that carbon always forms 4 bonds and we kind of assume hydrogens at every possible spot, this literally becomes just that, like a line. And every point of the line is another carbon with hydrogens at every possible spot, unless we put other things in there that shows us other things. So like each sort of point is another carbon. This one here, we can just represent this like that. Literally, just that. 1, 2, 3 kind of points of my line, if you will, and that means 3 carbons, and we know that carbons are every possible spot. This guy right here, let's see if I can draw this off to the side. 1, 2, 3, 4 carbons, so I could go like 1, 2, 3, 4, like that, make a little zigzaggy thing like that. And then this carbon right here, I didn't I didn't draw this in the best way, but I could do it like that. Trust me, these two things are the same. We'll get into that. Basically, this one, this is just flipped upside down. But 1, 2, 3, 4 carbons plus another little carbon sticking off right here. So you can see organic chemists are lazy. Like, we don't want to always be drawing all this, especially with really long molecules. It gets to be a lot of work. So we've stripped it down to just the skeletal structures. If the skeletal structures are kind of blowing your mind, it's definitely not an absolute necessity that you know how to draw them per se. We should be able to recognize them at least. And we'll talk more and practice more about this in class. So, and especially if on organic tests you'll be asked to draw organic molecules, skeletal structures are not acceptable. You need to be able to recognize them. Like I said, full structures or condensed formulas are acceptable. Basically anything that represents all the hydrogens in some way, and we'll go back over this in class about what's acceptable versus not. But skeletal structures, recognize them, but don't draw them that way yourself on like a test or a quiz or something like that. Okay, so naming. Here we're going to start diving into the naming of organic molecules. It's complicated. You know, it's going to seem really weird and complicated to you at first, but honestly, if you think of how difficult of a job, basically the name in words of an organic molecule has to unambiguously produce its structure. And considering how difficult the task is, I think they actually did, the good people at UPAC, did as good of a job as they could do, really, to develop this naming system. So I'm going to go over just the really general type rules, and we're going to look at some examples, but these are just the very broadest type rules of the kind of things you want to think about when you're naming stuff. Pretty much always, with one exception, one of the first things you're going to do is you're going to try to find the longest chain of carbon atoms you can without like taking a left or a right or kind of breaking up your pathway. That is going to be considered the main chain. And then, again, in almost all cases, the name base is going to be kind of based off of that. The carbons that might be sticking off of that are considered side chains. We might have multiple bonds, we might have functional groups. We're going to number them such that we give these things the lowest possible numbers possible. So we're going to give side chains and multiple bonds and or functional groups the lowest possible number we can. And in fact, functional groups have numbering priority over side chains, and they're going to get the lowest possible number. We'll go back over this when we specifically talk about functional group naming. We're going to start with just hydrocarbons, but that's going to be relevant when we get back into the functional groups. And you're gonna name the functional group suffix. Functional groups mostly are named using suffixes, things on the end. Side chains are added as a prefix, and again, I just want to kind of breeze through these rules and so that you have them, and then we will go back and look at some examples, of course, quite a few. Side chains are typically named with prefixes. Molecules can have 2 or more. Each is named separately. I'm going to have a slide here that's going to tell you what these numbers mean in just a second. But meth is associated with 1, eth is associated with 2, and propyl is associated with 3. So side chains are added as a prefix before the word. Carbon-carbon bonds change the end of a name. So like we talked about, alkane, alkene, alkyne, that's kind of being reiterated here. Single bonds, if there's no double bonds between carbons, is associated with the ane ending. A double bond is ene, and a triple bond is yne. We're going to use di or tri to indicate 2 or 3 of the same group, and we're going to say the carbon number for every group that it's attached to. And again, this is way easier seen by looking at examples, and momentarily we're going to look at some. So organic chemistry is famous for requiring a lot of memorization. The very first thing you should memorize is this. And here, let's get real for a second here, folks. You need to be diligent and keep up with this stuff. And if I tell you you need to memorize something, you need to memorize it, and you need to make every effort to do it as soon as possible. Because if you don't, stuff is going to stack on top of each other, and it's going to get really, really ugly really, really fast for you. So these things, you need to memorize these right now. Like, as soon as you possibly can. I'd even stop this video for a second and maybe study them a few times and just start thinking about them. I'm going to also have you make some flashcards, not for these things specifically, but we're going to make flashcards. We're going to do all kinds of things to help us, but this is the very first thing that we need to talk about and memorize right here, which is the words that refer to numbers of carbons. So meth is 1, eth is 2, prop is 3, but 4, pent 5, hex 6, hep 7, oct 8, non 9, and dec 10. Some of them are familiar: pent, hex, dec, if you think of like decade and so forth. But the other ones are a little weird. Hex, I guess, hexagon, that's pretty good too. But the eth, prop, all that sort of stuff, those get a little weird, and you definitely don't want to be the reason you're failing your organic chemistry courses is because you mix up like prop and but. Okay, so here's some examples. All right, so this one right here. Now, as far as like writing all these down in your notes, I wouldn't necessarily do that. Maybe you want one or two. There is a ton of examples and practice in your workbook, so you don't need 50 million examples. I would just maybe write down one or two, and then you can concentrate on looking at other examples in the workbook. So the very first thing we do, like I said, is we find the longest carbon chain that we can and count them. This one is a very straightforward one. 1, 2, 3, 4. There's no side chains or anything. And so the thing for 4 is but, and there's no double bonds or anything like that, so it's ane, so that's butane. That's all it is. All right, now here's another one that's a little bit fancier, and let me try to show you on my whiteboard here kind of what we're doing. Okay, so I have the same molecule drawn here, and our first job is to count and see how long we can count without having to like break our chain or lift our finger or whatever. And so, for example, I could go 1, 2, 3, 4. I could do that. I could also go 1, 2, 3, 4. I'll get more to that in a minute. Or I could go 1, 2, 3, 4. I could number them in that direction. So I could do it a variety of different ways, but definitely the most I can count is 4. So I know that this is going to be named as a but. That's going to be the kind of main name of this thing. Now, notice I have in green and in orange 2 different ways of numbering this thing. I could number it from in this direction, 1, 2, 3, 4, or I could number it in this direction, 1, 2, 3, 4. I could also do this, but I'll get to that in a second. So here's how you decide, because we do have to assign numbers to these carbons. How you decide is, I'm going to give this, which is considered a side chain, I'm going to give this the lowest possible number that I can give it. So in other words, if I number, what I mean by that is the carbon that it's attached to, I'm going to give that the lowest possible number that I can. So notice if I number them this way, this is carbon 3, and this thing is attached to carbon 3. If I number them this way, it's attached to carbon 2. So that's what I'm going to do. I'm going to use the orange numbering when I number this thing and when I name it. So 1, 2, 3, 4, it's a but. This is considered to be a side chain because it's broken off, it's apart from the main chain. And in the side chain, there's only one carbon. The thing for 1 is methyl. So that's a methyl group. And I apologize about the bells. So there is a methyl group here on the second carbon. These things are named as prefixes. It's on the second carbon. It's methyl. So this is 2-methyl-butane. 1, 2, 3, 4. Butane, because this is 4. 2, because it's on the second carbon, and it's a methyl group, so it's 2-methyl-butane. I want you to notice something, because I could have gone...
Students, you should be heading to your 3A class.
Sorry.
If you're not going to 3A class, you are welcome to go to the
I mentioned before...
or take a break and step outside and relax for a little bit.
You could number this like some different, like for example, I could number it like this: 1, 2, 3, 4. And notice that's a different way of numbering, but notice that it's still 1, 2, 2-methylbutane. Even when I number it like that, it's still 2-methylbutane. So as long as you do that thing where you find the longest possible chain of carbon atoms and give this methyl group the lowest possible number, it will always work out, even if there's some different sort of like variations in the way that you would number it. And I know this is going to be a little mind-blowing. We're going to look at some more examples. Let's just look, actually, let's look at this one that I have up here while I've got this. So, okay, the first thing I want to do is try to count all different ways. What's the most number of carbons I can count? I can count 1, 2, 3, 4. I can do that. And again, without like lifting my finger or breaking the chain. 1, 2, 3. Well, that's only 3. 1, 2, 3, 4. I could do that. 1, 2, 3, 4. 4 is the most I can count. So there's going to be a main chain here of 4. So again, it's going to be some kind of butane. And I'll circle this in orange. So this is the part that's going to be considered the main chain. And now there's 2, what we call side chains or side groups here. And I need to tell the person where both of those are. Because depending on where they are, it's going to have different names. It's going to affect its properties. So I'm going to number these carbons. I could number them 1, 2, 3, 4, or 1, 2, 3, 4. I'm going to make that choice. Whatever is going to give these the lowest possible numbers. Now in this case, it doesn't matter. So this is carbon 1, this is carbon 2, this is carbon 3, this is carbon 4. If I number it that way, these are on carbons 2 and 3. Or even if I number it the other way, so if I start right here, 1, 2, 3, 4. And I could number it some other ways too. It's not going to matter. If it's always going to be a carbon on the second and rather a methyl group on the second and third carbon. So this is the butane. That's its main name. It has 2 side chains. Those are prefixes. Because there are 2 of them, 2 methyl groups, it's going to be dimethyl. You always have to use a prefix to say how many methyl groups are there. So, and they're also on carbons 2 and 3. So get this. This is 2, 3 dimethyl, 2 methyl groups, 2, 3 dimethyl butane is what that's called. And again, I know, a little crazy. We'll look at some other ones here. This one we already did, 2-methylbutane. So this is the one that I was just showing you. We have a butane here. We have 2 methyl groups, that's why di, on the second and third carbon. And again, notice if I number it, even if I number it like 1, 2, 3, 4, like that, it's still carbons on this. It's still methyl groups on the second and third carbon. Now look at this one. Notice again, 1, 2, 3, 4. So 1, 2, 3, 4. I try to count all different ways. 1, 2, 3, 1, 2, 3, 4. So this again is yet another butane. Now there's also 2 side chains. So let's consider this part to be the main chain right here. I apologize, my pen is broken. Otherwise, that's why I'm using the board. Otherwise, I'd be marking right on the screen here. So let's consider this to be the main chain and these 2 guys to be... So again, this is dimethyl because there's 2 methyl groups, this one and this one. But the difference between this one and this one is in this case, both of those methyl groups are attached to the same carbon, and in this one, they're attached to consecutive carbons. So these things need different names. How we do that, that's the whole point of saying what number the methyl groups are on. So instead of 2,3-dimethylbutane, this is 2,2-dimethylbutane. 2,3-dimethylbutane, the methyl groups are on consecutive carbons. 2,2-dimethylbutane, they're on the same carbon. So again, our name must unambiguously produce this structure. So we say di to indicate there's 2 methyls, and we say 2, even though both of them are on 2, we say 2 twice. And I know some of these rules seem a little weird, but they're all there for a reason to unambiguously produce the structure from the name. We'll look at some more examples. Okay, so again, what you want to do is you want to look and find the longest possible number of carbons you can in a row. So 1, 2, 3, 4, 5. So I count 5 if I do that. Try this, 1, 2, 3, 4, 5. So I do get 5 if I go down that way. Don't forget about things like this though. 1, 2, 3, 4, 5, still 5. Okay, so it's definitely going to be a pent. But yeah, make sure you check all the possibilities. So it's going to be a pent, 1, 2, 3, 4, 5. So then I've got this, which we're going to consider the side chain. Now notice this time, unlike in the last ones, the side chain only has 1 carbon. In this case, the side chain has 2 carbons. So instead of a methyl group, that's an ethyl group. And notice there's a difference between 2 different methyl groups, right? This has 1 carbon, this has 1 carbon. Yeah, there's kind of a total of 2 carbons like sticking off to the side, but they're in separate places. Whereas here, there's 2 carbons and they're in one place, if you will. So we're going to call this an ethyl group. We're going to give it the lowest number we can. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 3 is the lowest number we can give it. This is 3-ethylpentane. Now, I'd like you to notice, even if we decided we're going to count it in a weird way like this, watch. 1, 2, 3, 4, 5. It's still 3-ethylpentane. So if there's multiple possibilities, as long as you focus on that thing of giving it the lowest possible number, no matter how exactly you number these carbons, it's still going to generate the same name. The only way that will get screwed up is if you don't start out by finding the longest possible chain of carbons. Or even this, 1, 2, 3, 4, 5. Even if I count it that way, it's still 3-ethylpentane. So as long as you find the longest possible chain you can, and you you give things the lowest number that you can, then you're going to be okay. Now this one, take a second and see if you can figure out the name for this thing. So let's do it. Let's count. Now it's tempting. 1, 2, 3, 4, 5. Say, oh, this is a pentane. But we need to check this possibility. It's actually not a pentane. The longest carbon chain is this thing that goes around like this. 1, 2, 3, 4, 5, 6. This is going to be named as a hexane. And this is going to be a methyl side group. Okay, so 1, 2, 3, 4, 5. If you try to call it a pentane, that's incorrect because it's not the longest possible chain. So we could either number the carbons 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. I'm going to number them this way because that puts the methyl group on carbon 3, which is the lowest possible number. It's a methyl group because there's only 1 carbon in the side chain, as opposed to this where there's 2 carbons in the side chain and it's ethyl. So this is 3-methylhexane. 3-methylhexane. Okay, here, now we got a double bond. That's going to change our ending. Instead of an ane ending, it's going to be an ene ending. Now, we do also need to say where that double bond is, because the double bond could be here or it could be here. This is actually the same as this. We'll talk more about isomers and stuff later. But 1, 2, 3, 4 carbons. 1, 2, 3, 4 carbons. We're going to give the start of that double bond the lowest possible number that we can. This seems a little weird having a number in the middle of a name like that, but that's what you do. You say the number right before the double bond, so that's but1-ene. Now, in truth, you will sometimes see this referred to as 1-butene instead of but1-ene, but in the IB world, they seem to always do it this way. So I'm putting a number because giving it the lowest possible number, the double bond starts, it's where it starts on carbon 1. Okay, so then we look at this. Still, same rules apply. 1, 2, 3, 4. 1, 2, 3. 1, 2, 3, 4. So I can't count any longer than 4. And then the next question becomes, am I going to go 1, 2, 3, 4 like that, or 1, 2, 3, 4 like that? So I'm going to call this carbon 1 because the double bond gets numbering priority over this, which is a methyl group right here. Okay, so it's some kind of butane. There is a double bond on carbon 1, so it's going to be a 1-ene, but then there's a methyl group here, which is on the 3rd carbon, so it's 3-methyl-but1-ene. 1, 2, 3-methyl-but1-ene. Okay, ooh boy, let's look at this one. Let's find the longest number of carbons that we can. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. So 6 seems to be the longest number of carbons that we can get. And also, don't do things like put double bonds in the side chain and things like that. Sometimes that might be possible, but we don't have to name things like that. So put your functional groups and stuff within the main chain if there's a couple of options. Oh, there's also 1, 2, 3, 4, 5, 6. Yeah, like we could number it like this. But don't do that because that's going to put this weirdness as a side chain. So try to make your naming job as simple as possible. So I'm just going to do this kind of straightforward one here as the main chain. Now we got a couple things going on. We got a side chain that's 2 carbons long right here. That's an ethyl group because connected to this carbon there are these 2 carbons. And we got this, which is just a methyl group. So this is going to be an ethyl group, this is going to be a methyl group, and then we got this double bond, and that all needs to be part of the name. This gets numbering priority. Double interval bonds get numbering priority over these. So this is going to be carbon 1. 1, 2, 3, 4, 5, 6. So this is 4-ethyl 5-methyl hex 1-ene. I know, crazy, crazy, crazy. Hex 1-ene because it's a hexane, because it's 6 long. Hex 1-ene because we're going to give that double bond the lowest possible number, which is starting on carbon 1. So 1, 2, 3, 4 ethyl 5-methyl hex 1-ene. This one has 2 double bonds. 1, 2, 3, 4, 5, 6. Just like with the other functional groups, it needs a di. And so it's hex 2,4-diene. 1, 2, 3, 4. It's where the double bond starts. Hex 2,4-diene. So whenever there's 2 of something, 2 of the exact same thing, you always need a di. You always need to say where both those things are. Now, as I said, this is on my water bottle. And as you learn more organic chemistry, you can actually understand some more of these fun chemistry jokes. So here we have 2 skeletal structures. Before organic chemistry exam, after organic chemistry exam. I'm dying. Get it? Because he has 2 double bonds there. All right. Triple bond. That's Y-N-E. Other than that, it works the same as the other ones we've talked about with the double bonds. So give that one a shot. 7-methyl oct-2-ine. 1, 2, 3, 4, 5, 6, 7. The methyl is on the 7th carbon. The ine is on the 2nd carbon, or it starts. The triple bond starts on the 2nd carbon, so that's why it's 7-methyl oct-2-ine. Woo-wee! This is a fun one. This is your, final challenge. It's probably definitely a little harder than anything you'd ever actually have to name on like a test or a quiz or something. But give this one a go. Okay, so it is 4,5-diethyl 6,7-dimethyl oct-2-ene. Woo! By the way, if you had these in like a different order, you name these in alphabetical order. Eth becomes before meth, and that's why it says. So if you said 6,7-dimethyl 4,5-diethyl, that's fine for now. But the numbering priority is going to be here. So 1, 2. That's why it's oct-2-ene. 1, 2, 3, 4, 5, 6, 7, 8. So carbon 2. And then on carbon 1, 2, 3, 4 is the first ethyl group. 5 is the second ethyl group. And then carbon 6 and 7 have the methyls. That's why it's 6,7-dimethyl, and it's oct-2-ene. Okay, guys, I know that's super crazy, but thank you so much. We'll talk more and work more about it in class, and we'll see you again soon. Thanks for watching.